Hey, welcome back to Math with Patrick. Today is February 15th, and we're solving problem number 46 from this Daily Epsilon calendar. We have an integral today. Okay, looks like we solve the integral, get whatever the value for y is, and then e to the power of y gives us x, which should be 15. Let's see, so our integral goes from 2 to 9, and we have a fraction. My numerator is 2t plus 1, my denominator is t squared plus t, and we are integrating with respect to t. Okay, I kind of already see the path forward. U substitution is a really good strategy when you can see a chunk of stuff whose derivative is also in your integrand. So if I let u to be equal to t squared plus t, and then I try to take the derivative of u with respect to t, then I get 2t plus 1. Great. And then for like Calc 1 and 2, you can generally treat these differentials as fractions. I know it's not like best practice, but it won't fail you during like taking single integrals or single derivatives. So you can imagine this dt kind of scooching over here as if you multiplied it over to the right side. And so just du is going to be the same thing as 2t plus 1 times dt. I guess I should put parentheses here, kind of like that. And now I have my substitution all set up. Let's see. So in my denominator, I have t squared plus t. But 2 seconds ago, I just said that that was the variable u. And then in my numerator, I have 2t plus 1. And again, when you're kind of thinking as if these were fractions, if you have like 3/5 times 4, the process to multiply them is just take the numerator and whatever you're multiplying by. So I can grab both of these things and just call it du, because I did all that work, found a derivative, and all of this part right here just simplifies to a du. Now I could put that in the numerator, but I just prefer to have a 1 over u and then my differential off to the side. It would be totally fine to write it as du over u. It's just not what I prefer. The last part is I need to also change my bounds. I mean, technically I don't. There is a way to, do this integral and then go back and change it back in terms of t, but whenever I'm doing a definite integral, which is one with bounds, I just like to change all of my numbers from numbers in terms of t to numbers in terms of u. And this rule that I created, u equals t squared plus t, helps me change this 2 into a better number for my u's over here. So if I plug in a 2, I get 2 squared plus 2, which is 6. And that will be my new bound in my u integral over here. And then 9 squared plus 9 is 81 plus 9, or 90. And there we go. I have changed all of my values in terms of t, now into values in terms of u. And this right here is a very familiar integral. This is just the natural log of my input, and then evaluated from 6 to 90. Usually here you do need absolute value bars, but in this case, since my input's already positive, it doesn't really matter. Great, so I can now evaluate it at 90, so natural log of 90, and then subtract what you get when you evaluate it at the lower bound. This right here is just like the fundamental theorem of calculus. You can find an antiderivative, plug in your bounds, and then this right here is y, because y is equal to this whole integral. So right here is my y. But I could simplify this one step further, actually. There is a logarithm property where if you have a log of a difference, it's the same, or difference of logs is the same as the log of a fraction or a ratio. And you could verify this yourself. You could like plug this into a calculator and try it this way and try it that way, and they're going to be the same number. And this just helps me simplify it a little bit more, because I know that 90 divided by 6 is just 15. So, and you could even try this too. Natural log of 15 is going to be the same as natural log 90 minus natural log of 6. So there is my nice and simplified version of y. I know that x is equal to e to the y, which is natural log of 15. And at this point, I feel like most people would just say like, yeah, they cancel, and just cross off these things. But at least when I was learning logarithms, I wasn't sure like why that was the case. And I'll try to convince you before I actually just cross them off. This expression right here, natural log of 15, asks e to what power gives me 15? That's just kind of by definition of what a logarithm is. Like if I asked log base 2 of 64, this is asking 2 to what power gets me 64. You could just count by your powers of 2, and 2, 4, 8, 16, 32, 64. And then you'd eventually hit 64. So this number is just a 6. Anyways, logarithms ask how many of my base do I need to multiply all together to hit my target number. And I'm not quite sure what this number is. I know that e is about 2.71. So like kind of rounding that to a 3, e squared is going to undershoot 15, and then e cubed is going to overshoot 15. So this value right here is somewhere between 2 and 3, but it doesn't actually really matter what it is. It is the one unique number that when I raise e to some power, I get 15. And whatever that number is, I am raising e to that power. So e to this mystery number gives me 15, and so just kind of working through it that way, x is 15. And that's my answer. When you're working through this algebraically, usually just crossing these off is fine, but I at least wanted to maybe convince you that you can just do that. I also wanted to share some kind of like graphical understanding of integrals. We were first given, let's see, I'll use x for my input, 2x plus 1 over x squared plus x. And so we were asked to take the integral of this kind of wacky rational function. And what it looks like on the graph is taking the area underneath this curve and above the x-axis from whatever our bounds were, which were 2 to 9. So this area right here was that 2 or 3, like between 2 and 3, that we found, which was natural log of 15. Okay, so the area here is about 2.7. And maybe I can convince myself of that because looks like our length here is 7. Our height, I'm just trying to visualize an average, would be maybe a half. And if I think of it as a rectangle, half times 7, okay, I kind of overshot it, but the area is around 3. And the other integral, the one that I actually took to get natural log of t earlier, this one was just the 1 over x, a pretty standard rational function. And those bounds were 6 to 90. And that's this one over here. And this one will go on for a long time because the upper bound is 90. But as you can kind of tell, the amount of area between the curve and the x-axis is kind of minimal over here. I'm looking at that value on the right there in the ordered pair, that 0.01. Basically, it's about a 100th of a unit away from the x-axis. So it's so close to 0. And hopefully you can convince yourself that this long, short area is going to be the same as this taller but more narrow area. And either way, we get natural log of 15 as the area under both of these curves. Not together, but each of them are natural log of 15. And then when we did e to the power of natural log of 15, they do indeed cancel out, and we just get that 15 as our answer today. Cool. X is 15. We're all done. I'll see you tomorrow. Bye-bye.